Hi again. In the previous video, we looked at what the spectral irradiance, what the total irradiance, and what the power is we get by the sun at different locations on Earth. Now I would like to come back to this power and start considering, so what can we gain in terms of electricity? Because at the end, our aim is to generate electrical power out of solar power, or electricity out of the energy of the sun. And in this video, I'm going to show you the basic definition of what efficiency, and we are going to look at how it is calculated. So let's get started. So we have these power values available now, and now we want to know what is the efficiency of our solar cell, or the other way around, we have a solar cell, know the efficiency, and want to know what electricity, what electrical power can we expect. And in order to do this, we have to first of all define the efficiency, which is given the Greek letter eta here. So the efficiency eta is defined as the power that is extracted from the solar cell, so the electrical power, divided by the incoming solar power. And in order to look at what electrical power is extracted, we can consider our solar cell here in an electrical circuit. So our solar cell is illuminated by an incoming solar power, and then we have some load in the circuit. I just called it here a consumer resistor to model all of the consumer. This can be a small consumer or a big consumer, depending if this is just a tiny calculator solar cell module, or if this is a huge solar module that can support a whole house, for example. But either way, I just all the consumer is summarized here in this one resistor, R consumer. And now if we want to operate this consumer with the solar cell, we are utilizing the energy that is generated by the solar cell, in a sense that the solar cell pumps a current through the consumer, and this with a certain voltage. So if you characterize the output of a given solar cell, you can measure what is the voltage, what is the current that the consumer has, and then you can calculate the power you are supplying the consumer with by multiplying the voltage U by the current I. And this gives us the power that is extracted by of the solar cell, and that is used by the load. So the used power is U times I, the incoming power is P inc, and therefore our efficiency eta of conversion from sunlight to electrical power is dividing the two. So dividing the electricity, the electrical power by the sun power, and that is our efficiency. And so this is quite straightforward. If you have a solar cell and it is running, you can basically measure what are I and U, and then you can measure what is the incoming power, and then you know at what efficiency your solar cell is running. Of course, often you want to run the solar cell at maximum efficiency. You don't just want to run it at some efficiency, but you want to maximize this eta. You want to get the maximum electricity out of your solar cell. And what we can see from this simple image here is, if you want to change at which current voltage pair the solar cell is running in order to maybe get a better efficiency and more power out, that means you have to change the consumer. So in order to run at the maximum power point, you need to change the external load, you need to change the consumer here in order to adjust the current to the current of the maximum power point and the voltage to the voltage of the maximum power point. And So therefore, if you are at this maximum power point for your solar cell, then we can define the eta MPP, that is the maximum power point efficiency. So if you have done all the adjustment of the load, practically then you're at your maximum power point, and that is then the maximum efficiency you can get out of the given solar cell. This maximum power point depends on the illumination condition. So we have seen that the solar energy is changing as a function of the day and the year. So that means if the power of the solar cell, the incoming power on the solar cell is changing, also typically this maximum power point is changing. So you need to adapt the load in order to always run your solar cell in the maximum power point. And you can see that you cannot do this by just changing the solar cell, but you have to do it by changing the consumer, the load that you have on there, not necessarily the consumer. You can also use power electronics in order to adapt the solar cell to the consumer, to the load you have, and that's what you typically do, that you have a power electronics in between here. But what we see from this resistor, this load, needs to be adapted if you have a changing illumination of your solar cell. And this is called maximum power point tracking. And in order to extract the maximum efficiency out of photovoltaics, it's essential to do maximum power point tracking. Because otherwise you would maybe be by chance at the beginning at a good condition, electrical condition of current voltage pair, but you might run out of it if the sun is setting or clouds are appearing or other illumination conditions are changing. So therefore, you need to adjust the external load. So let's consider one more figure of efficiency or of merit that is often used for solar cells, and that is considering the quantum flux. So let me first of all define what the quantum flux is. So we were talking about the maximum incident power that we have. Of course, for the given power, you can also calculate how many photons phi incoming are arriving. So you can actually count how many photons are arriving on the solar cell. And I remind you again of the wave-particle duality of light. So here we need to consider light as photons, as packets of energy, and then we can calculate how many of these photons arrive on the solar cell. And that is the phi incoming. And in order to calculate that, we have to consider how many photons of different wavelengths are arriving. So the phi lambda is the number of photons per wavelength interval. Again, we need to integrate over all the different wavelength intervals in order to get the total flux. And then this photon number per wavelength interval is actually related to the spectral irradiance L lambda, just by dividing L lambda by the photon energy, so how much photon each individual energy has. And also to get the total number of photons, we need to multiply with the area. So here the total number of photons is given in photons per second. So it doesn't have the it doesn't have anymore the per meter squared, so therefore we need to multiply with the area of interest in order to get the photon number per second. And we can also plug in the photon energy. We have seen in a previous video that the energy of a photon at a wavelength lambda is given by the Planck constant times the speed of light c divided by the wavelength lambda of the photon. So we can also plug this in. And so this integral here gives us then multiplied with a, gives us the total number of photons that are incident onto the solar cell. Of course, not all of these photons need to be absorbed by the solar cell, so only a part of the photons is absorbed, and this part I call phi ABS for absorbed. So phi ABS is the absorbed number of photons. So we have an incident number of photons and we have an absorbed number of photons. And then these photons generate an electron current I in amps, in ampere. And this electron current I then can be related to the number of electrons we have. So phi E is the number of electrons, and it's given by the current I divided by the elementary charge Q. So the phi E is how many electrons do we have in our solar cell per second. And therefore, we can then define a quantum efficiency that relates the number of electrons to the number of photons. And we distinguish between two different values. One is the external quantum efficiency. This is giving phi E divided by the total number of incident photons, and it's called eta EQE for external quantum efficiency. And the internal quantum efficiency divides the number of electrons by the number of photons that are actually absorbed in the solar cell. Because part of the photons is not going to be absorbed, it's just passing through the cell, or it is reflected maybe. So the internal quantum efficiency only considers if I have a photon that is absorbed, how many electrons are generated. And so these two quantum efficiencies are also often used if you're considering efficiencies of solar cells. In particular, if you want to understand how a solar cell operates, the quantum efficiencies are important. So to summarize, we have these three different efficiencies defined now. We have the power conversion efficiency that relates the extracted power to the incoming power. We have the external quantum efficiency. This relates the number of electrons that are generated to the number of photons that are incident on our solar cell. And we have the internal quantum efficiency. This is dividing the number of electrons by the number of photons that are absorbed. There are other efficiency values, and we will actually look at some more later on in this course. And these are particularly related to the maximum efficiency that is possible with solar cells. For example, the theoretical thermodynamic limit is called the Shockley quasar efficiency, and we will look at this one later. Besides these efficiencies relating the power or the number of photons, there are of course also other key figures to consider in the context of solar cells. For example, the energy payback time is important. It relates to how much energy is needed in the production of the solar cell and how much energy is generated by the solar cell, and thus how long does it take until the energy that was needed in the production is actually generated by the solar cell. This is of course for the environment an important figure, because only when we have reached the energy payback time afterwards on a global scale we will have a net win of energy. And on the financial side, for example, the amortization period is important. So how long does it take until the cost of the solar cell has amortized itself? Thanks for watching.